Hi guys, let's finish up our study of kinetics with lesson 2.3. This is video 2.3.1. Alright, so first let's review collision theory. Now collision theory, you should have learned before, but we're just going to review the three parts of it. So in order for a reaction to take place, the molecules actually have to run into each other. They need to collide. They need to do that with enough energy. And they have to do that in the correct orientation. Because if they're not lined up the correct way, they're not going to be able to react. So let's write down those three parts. A reaction takes place when molecules collide with enough energy and in the correct orientation. Okay, so we know that those three things have to happen for a reaction to take place. And we can speed up the rate of a reaction, or how fast a reaction happens, mainly in 5 ways. So we can increase the concentration of reactants. So if we increase the concentration, we increase the amount of molecules that are present, and the more likely they're going to be to bump into each other, and the more likely they'll be in the correct orientation because there's just more collisions. We can also increase the pressure, which will do the same thing as increasing concentration. And this specifically is helpful for gases. If we increase the pressure of gases, we push those molecules closer together and they're more likely to collide. You can increase the surface area. And this is mainly for things like solids. So for surface area, you can think of sugar cubes and sugar as an example. Sugar cubes have much less surface area, or much less area on the outside than like powdered sugar, for example. So if you were to take some solid and grind it up, you would be increasing the surface area. And that increases the area that's available for reactions to happen. So you can increase the area that's available for collisions to take place. You can also increase the temperature. And when you increase the temperature, you are adding kinetic energy to the molecules. So when they do collide, more of them will have enough energy to actually react. And lastly, you can add a catalyst. And in biology, those catalysts are called enzymes. Those are biologically specific catalysts. And those actually provide a completely different pathway for the reaction to happen. We'll take a look at those in just a minute. So let's look at a potential energy graph. We're going to consider the reaction A goes to B plus heat. So this is going to be exothermic. Because heat is produced, it is exothermic. You're producing heat, you're giving off energy. If the heat was on the left side, if it was on the reactant side, that would be endothermic. So we're going to sketch a potential energy graph of A going to B. Now, since I know this is exothermic, my A is going to start somewhere up here, and B is going to start here. These are arbitrary. As long as B is lower than A, you're good to go. So then you have a little hump here, and we'll explain what that is in a minute. And there's your reaction progress. Okay, so this is going to be A. This is going to be B. And this is going to be some activated complex. Activated complex. You'll also hear it referred to as the transition state. So that's some state between A and B. And you can see that it's at a very high energy level. So it actually doesn't exist for very long. So there has to be a lot of energy put in, and then you get up to some activated complex here, and you form some compound temporarily that's just super high energy, and then that energy is all released as that activated complex turns into whatever your products are here. So the question is asking us to label the potential energy of A, the potential energy of B, and the potential energy of the activated complex. So we're just going to do that. Potential energy here is on the y-axis, so this right here, potential energy of A. And this is a potential energy of B. Really, it's right here, this energy level. The activated complex has a really high potential energy. So this is our potential energy of the activated complex. Okay. The activation energy, that is the energy that it takes to be able to get from A, or your starting reactants, all the way up to your activated complex. And that is the energy it takes to get your reaction started. And so this is abbreviated E sub A. So this is our EA, our energy of activation energy. So this is that energy, we say with enough energy here, it has to have the EA. It has to have the activation energy required to get up to the activated complex. And the enthalpy of reaction, enthalpy, let's use different colors so you can see the difference. The enthalpy of reaction, enthalpy is another word for heat. Heat of reaction. So here, the difference between A and B, the difference in energy there, was given off as heat. So this amount from A to B here, that is going to be our enthalpy, or heat of reaction. Because that's the difference in energy, and that was given off. So that was given off as heat. Okay, so now what happens here when we add a catalyst? It says use a dashed line to indicate what happens when a catalyst is added to the reaction mixture. So when you add a catalyst, you actually are providing an alternate pathway. So A is going to start in the same place here, but then you have a much lower activation energy, and B ends up at the same place. So the dashed line is going to be here in green. So that's what happens when you add a catalyst. You actually provide an alternate pathway with a lower activation energy, and so more molecules are going to be able to have that less energy right there to get over that activation hump. So they don't have to have that much energy, now they just have to have that much energy. It's much less. So it provides an alternate pathway. An alternate pathway with a lower activation energy for the reaction. All right, from this graph, how does the increase in temperature speed up the reaction? So here, if you increase the temperature, you're increasing the energy. And so if you're increasing the energy, more of the molecules will have enough energy to get over the activation energy hump there. So more molecules will collide with enough energy to overcome the activation energy. Okay. All right, so now let's look at a different kind of graph, the kinetic energy distribution graph. We're going to sketch the distribution graph of kinetic energy of collisions for a reaction at some particular temperature. So this looks kind of like a skewed bell curve. So you're going to go up, and then you kind of spreads out like that. Okay, so your average is going to be here. It's going to be skewed more to the left. So we're going to label a few things. So it says, sketch the distribution graph, identify the average kinetic energy or temperature. Right here at the height, so this is our kinetic energy, this is the number of collisions. The average kinetic energy is right at the top. I guess it should have been over just a little bit more. But anyway, that's our average KE, or kinetic energy, wherever the highest point is on the graph. Okay, and the threshold energy. The threshold energy is going to be here. We'll just say arbitrarily. Threshold energy. And the threshold energy is the energy that the molecules have to have in order to react. So they have to have at least that much energy. So here, only this amount of molecules actually has enough energy to react, because they're the only ones with enough energy past the threshold energy. Okay, now we're going to use a dashed line to indicate what happens when a catalyst is added and the temperature is increased. So here, this is what's going to happen when you increase the temperature. So let's go here. So this whole thing kind of just spreads out a little bit more. Okay, so if we increase the temperature, just increase the temperature alone, then we have more molecules that have enough energy to get past the threshold energy. Now this many molecules have enough energy to react. Well, what happens then when we add a catalyst? When we add a catalyst, we actually change what the threshold energy is. Because again, we are providing an alternate pathway for these molecules to react. So instead of the threshold energy being here, this is our new threshold energy. This is like EA. Threshold energy is like EA. And now, if the temperature is increased and we've added a catalyst, this many molecules now have enough energy to react. So we can see how we can increase the number of molecules that are going to react by just manipulating the temperature and also the adding a catalyst or not. Okay, so from this graph, why does the addition of a catalyst speed up the reaction? The catalyst lowers the threshold energy. So more molecules have enough energy to react. Okay, from this graph, why does increasing the temperature speed up the reaction? Well, you have more molecules now that are moving faster and they're colliding with more energy, so you have more molecules overall that are past this threshold energy and they're colliding with enough energy to react. Oops. Should say more molecules are moving. And colliding with more energy. So more molecules can overcome the threshold energy. No, it did it again. All right, and that is it for our review of the collision theory and looking at our potential and kinetic energy distribution graphs.